access. We have servers everywhere, but not a bit to flip. And this comic there is just to remind us that even digital data can degrade with time. So who am I? My name is Filipe Fernandes, but you will actually find me on GitHub and elsewhere as OCFPAF. I'm a physical oceanographer by training, but what I do most of the day can be called data plumbler, code janitor, CI babysitter, or Amazon Dash Pluton for Conda Forge. If you don't know anything about the other stuff that I do, that's great. It means I'm doing my job right, because I pretty much act on the background to make sure you all have access to data, good libraries, and good packages to do your science. My day job is at IOOS, the Integrated Ocean Observing System, which is breaking down into all these various regional associations. To be more specific, I actually employed by Secura, the Southeast Coastal Ocean Observing Regional Association. This is always a mouthful. So big or small, we need data, right? By the way, for those that are following the notebook, you're probably seeing there is a difference between my slides and your notebook. They're actually the same code and the same thing. If I do this, I will go back to the notebook, right? So that it's easier for you to visualize what I'm talking about if I do it using the slide mode. So we need data, and there are various sources: servers, API, web services. And just to list a few, we have OpenDAP, AirDAP, Threads, FTP, HTTP, S3, LAS. If you know what LAS is, welcome to the club. You're as old as me. It's probably one of the oldest way to serve data. And I see people laughing there. So yes, you know about LAS. It's the live access server. And most of the servers are like a house of cards. And that's why we keep switching to the next new shiny thing. On this tutorial, I'm going to touch on a few of those, mostly based on the data type and the web service that you're going to be using. For in-situ data, time series, trajectory, etc., we have like buoys, stations, gliders, Argo floats. We can use the SOS, which is an open geospatial consortium, and that has a response of either an XML or a comma-separated file, which we can load in pandas or even an X-array, for example. For gridded data, like models and satellite, the most common one is OpenDAP, which we can answer as a binary format, a self-describing binary format, pretty much in an etcdf format. Then we have raster images, again, an open geospatial consortium format. We have the WMS, it's the web mapping services. It can be a GTIF, PNG, or a JPEG. And last but not least, we have AirDAP. AirDAP has a RESTful API, where we can access the data in multiple formats. And I have the asterisk there because, yes, your imagination is the limit with AirDAP. And that suffices to say that we're actually switching a lot of those other services that I mentioned to AirDAP only. So what we're going to see in this tutorial, we're going to browse and access data from AirDAP, OpenDAP, SOS, WMS, and CSW. CSW is not really server, it's actually a server aggregator, and that will be clear if you can reach that. And as you can see, I put the most interesting first, because in case we run out of time, I can stop with the actual one single message that I want to leave here. AirDAP is the best way to access data nowadays. So AirDAP, what's our learning objectives? We're going to explore a service using the Python interface. We're going to find a glider based for a certain time and region of interest. We're going to download the data with a familiar format and create some plots. So what is AirDAP? Why I'm saying that AirDAP is so cool? Well, the best thing about AirDAP is its flexible outputs. Like I said, your imagination is the limit. If you want an HTML response, if you want an Esri ask file response, if you want a table as a comma-separated file, if you want a Google Earth KML, or even a MATLAB file. Yes, if you're a MATLAB user, you can get a MATLAB file as a response. You can have JSON if you're creating a web service that actually maps data live for a certain buoy or something. And then you have this RESTful API to access the data, which makes it very flexible on how you query the data as well. There are some standardizations that happens under the hood. The most important one is regarding the date and time results. So it's easy to ask for a time slice because it's standardized. The data may come with a certain time coordinate, but within AirDAP, they're all the same. They're standardized for you there. And then there's the server-side searching and slicing. And this is probably where AirDAP shines the most. If you are familiar with OpenDAP queries, you need to download at least the coordinates to actually slice your data and then request a download. And if that's a lazy download, but you still need to download all the coordinates. With URDAP, you don't need to do that. You request a high-level slice within the RESTful API. The slice happens on the server side, and then it creates a file that's served for you. And you only get that sliced file. So how can we do that? We're going to use the URDAP library, and pretty much we're going to initialize the server. We're going to ask for the TableDAP protocol. URDAP has two protocols, TableDAP and GridDAP. GridDAP is not supported yet with URDAP, but it will be soon. And then we can query things like what's available on the server. So I'm going to get a search URL using the comma-separated file response. And there you go. I have 753 TableDAP entries, 0 GridDAP and 0 WMS. So you can have WMS within URDAP. So let's query data sets. They have the trajectory profile CDM data type. CDM is the common data model. Now I can use things like the categorize URL to do that. So I'm going to categorize the CDM using the value trajectory profile, again, asking for a comma-separated file that I can easily load on pandas. And there you go, I have 752. So there's only one data set in there that's not trajectory profile, which makes sense. The server is for gliders, so they should always be a trajectory. So let's narrow down our search for deployments within a certain lat-long time extent. And here what I'm going to do before I actually do the search, I'm going to create a map within our bound box. So I defined this lat-long bound box, and I'm creating a map with IPy leaflet. By the way, if I'm going too fast through the code, it's mostly because the code here is not actually the code, it's how to get the data. You have the notebook, you have all the manuals for all these libraries, and you can ask any questions on Slack later, and I'll definitely help you to get this up and running. And there you go. So this is our area of interest, which is just a box of HOE. So we're going to browse for gliders deployed by the Oceanographic Institute. And I created a dictionary with my query. Here you go. I am querying data from 2016 and 2017 within that bounding box. I apologize if my dog is barking too loud. Hopefully the barks are not mating through. And now we can actually search again within only that space and time interval. And voila, instead of more than 700 gliders, I have 16 gliders, 16 data sets. So now it's getting easier to actually find data within our region of interest. So let's get one of those gliders. I just hard coded the data set ID, and I'm gonna request the following variables: depth, latitude, longitude, salinity, temperature, and time. And like I said, everything happens server side. So the only thing that I'm doing here is constructing the URL. I'm not really pinging the server for anything yet. And if I click on this URL, I can actually prove to you that it will take me back to the URDAP portal. It's just gonna take a while because my internet is a bit slow. Within that query, and I can modify my query here, I can see all the other variables that are not ticked, like this, the one that are ticked, is the one that I selected. But suppose I also want this precise time for some reason. I can just mark them here, and I can create my URL here. By the way, if you're not into programming, you can do everything that I'm doing using this interface. But if you're doing automatic stuff, or you want to automate a process, you definitely want to use this library. So instead of doing like I did before, requesting the download URL for the comma-separated file and feed it to pandas, I'm going to use a pre-built function in URDAP that throws my data directly into pandas. And I'm also telling it that the time column is my index, and I want it to parse the dates. So there you go. I have a table with the data that I requested. Now, like I said, they sliced HAP server side, and then they created a file for me, and then I downloaded the file. This is the only time where I actually hit the internet to get the data. I have some exercises, but in the interest of time, I will let you do them on your own, and please ask questions later. But there is another handy function there, or method, that's called toXArray. We'll do something similar, but instead of returning a pandas object, it will return a pandas object. And this makes sense, especially if you have GridDAP data. So let's just plot a track You have the code for this over there. I actually hid the code here in my slides because it doesn't make sense to show that. You had a Matplotlib introduction with Leticia yesterday, sorry. Come on, Friday. Quarantine is doing that with my time perception. I really don't know where I am anymore in time. So the only thing that I did here, I plot X and Y as scatter plots and the temperature to put colors on those circles. And then I can also create a track plot of the glider. Sorry, the previous one was a track. This one is a section plot of the glider. And you have two options. Actually, here you can either have X as time or distance, or maybe you can even do both. You were a pretty good Matplotlib user. But here, because the glider was kind of going circles, I decided that time was better to visualize what was going on with the data. And you can see a really nice mixing layer there. It's actually quite deep. I mean, 25. That area is a very interesting mixed layer. I forget the time of the year this is. And if you want to check the data for quality or for some spurious data, you can do a very quick TS plot. As you can see, the data seems fine, mostly because this data is QA/QC'd before it goes to the server. And like I said, imagination is your limit. You have so many outputs, so many responses in there that if you want a MATLAB file, you just ask for it. If you want a JSON, if you want an XCDF, or even if you want just a header, you don't want a file. Like this one is interesting if you don't want any data, but you're fetching metadata for your project. And those that are familiar with an XCDF file, you can see here there's a very common XCDF metadata dump, right? And for those that don't believe that you can get a MATLAB file, I'm going to click on here, and you're going to see that it's going to ask me to download a MATLAB file. How cool is that? I have another exercise here. So there's two main air-depth servers for gliders in the US. One's the one that I demonstrated, the IOOS one, and there's also the OOI server. And I would love for you to kind of repeat this kind of query, changing the time and the region, and find your own gliders of interest. And as you can see, you can either do the same server that I did, or you can use this one to get the OOI gliders. OpenDAP. So OpenDAP used to be the most common way to serve data. And they're usually behind a Fred server. And OpenDAP is still perfect for gridded data, like models and satellite images. Here, what we're going to do, we're going to hit a Fred server to make an OpenDAP query with Xarray, and then we're going to plot using the Xarray interface. This is actually the only reason why I'm coming after Deepak, because if I had to choose, I definitely would like to come before him, so I don't have to follow that act. So like he did, you can just provide the URL to Xarray, and then you have the Xarray object. In my case, it's not a nice HTML wrapper that he has there just because I'm on slide mode, but you should see that on the notebook. And like he said, you can do high-level slicing. I can just put here a date and a depth, and I have a slice data set for that time, for that selection. And then I can just call a variable to plot within that selection. If you really stop to think, we came a long way. Like I can, with 1-2 lines of code, slice a high-level data that have many dimensions and create a plot of the property. This is really cool. So the third one is SOS, which stands for, oh my God, I'm drawing a blank now. Sensor.
Observation
help
service.
me.
Sensor observation service.
Thank you. Yeah. This one is actually being phased out. It's a deprecated service. However, there is still a lot of data available in there. So if you're looking for some data that you cannot find in a NERDAP server or elsewhere, you may find yourself getting data from SOS. SOS URLs are relatively simple. You actually need to read the manual to understand all these entries, but pretty much it's a request, like get observation, the version of the SOS service, the name of the property, the name of the GUI in this case, or the dataset ID that's similar to their DAP, the format that you want back, and the time slice in this case, with the vertical datum and the data type. So if you read its API, it's not hard for you to construct a library that will do that for you. But Python is so easy that we don't need to construct a library. We can just use f strings to build that. And here's what I'm gonna do. I'm writing all the variables. I want get observation on this version. I want sea surface height. I want this buoy and all that. And I want the day of yesterday. So I use the time trick here to get today minus 1 day, so it's yesterday. And let's take a look at yesterday's data for that buoy. So I fill that same strings, but now they're f strings, and I fill them with these variables, and I get this URL. And if you're not convinced, I can click here, and because I asked for a comma-separated file, there you go, I have a comma-separated file. SOS is not as flexible as RDAP. You only have XML and comma-separated file. So I'm feeding that into pandas, and I have my table. A very quick plot of that, and you can see a very nice tidal cycle at this point, which, by the way, I have no idea where it is yet. So I can plot it by getting the latitude and longitude from that data frame that I got back. And that point is right here, near Providence. All right. So the fourth one is the WMS service, which is the web mapping services. To be honest, that's not really a way for scientists to get data. It's more a way for science to explore data. So it can get you a raster layer on top of your data so you can check if your model or your glider or your Argo, how is some sort of, how can I say, imagery. It can be temperature, it can be winds or whatever, how that is influencing your data. And this is what we're gonna do here. We're gonna create a hurricane visualization widget just using the WMS layer from my PyLeaflet. So I chose a few key times here, and I'm creating a slider that will update to that time every time I run the slider. And I'm gonna use the next run WMS later from the Agron AI state. And there you go. Now I have the map. Let me see if I can go full screen and back just to load the map. But now I have the slider here, and I can move the slider and see a new image here. The thing is, I ran this notebook earlier today, so I think it's not loading new data. But if you believe me, you should be seeing new images loading here instead of only just one. And you should actually see a hurricane hitting this area. If you rerun the notebook, you're definitely going to see that. My mistake here is that I ran this earlier today to record a video in case I had a power outage and I forgot to run it again. So, okay, I showed you AirDAP, I showed you SOS, I showed you WMS, and I showed you OpenDAP. But is there a canonical source of data? I don't want to really go to all those things separate. Well, not really. Or maybe there is, but it's not the best thing out there yet. We have catalogs, like CCAN catalogs, CSW catalogs. However, the interface to interact with them is not really nice yet. We can do, the best we can do is fast filters to filter data and feed them on a catalog web service from the web, from this library OWS lib, and query for those endpoints. So how these catalogs work? You have people collecting data and put on all those servers. And then the catalog harvests these endpoints every day using metadata, and then they feed those to the catalog. So for example, if you just get a new glider off the water and you put on your depth server, the catalog will harvest that and create metadata for us to browse it. And how browsing that works? It's similar to what we did so far. We have a latitude box with some extra metadata. We have a time interval, and we have, for example, here, various CS names with climate and forecast for temperature. So I'm gonna query for temperature within that latitude box within this time using all those names. So I create my filter. You have the actual details of the filter there in the notebook. I hid it here for brevity purpose. And I'm browsing the IOOS catalog. So now, as you can see, I found 170 records for temperature within that time span and that region. Just finding the records is not that easy. Like, I need to know what's behind there. So I'm gonna print the first record. It's NOAA IOOS SOS. Can I find what kind of URLs or servers those endpoints are? And here, unfortunately, my header here is hiding. You can use this library that's called geolinks, and it has a function that's called snifflink. We're gonna be sniffing the catalog for the types of data behind it. And as you can see, I have a lot of SOS stuff for that data. It's pretty much all SOS, with the exception of one OpenDep link. So that's what I said. Most of the data is still under SOS services. For a more complex example, we have a code gallery where you can find a lot of ways to query the catalog and find the data that you want. The main question that I usually get here is, should I always query the catalog to find data? And the answer is no. Once you find the endpoint, you keep that endpoint and you go direct to it, right? You don't use the catalog to find the data on your workflow. Use that once, you find the data, and then you always use the same endpoint. So where else to find data? We have a curated list of RDEP servers here. So the most important RDEP servers you're gonna find here. If you're looking for model data within the US, we have the EDS browser, a model viewer, where you can actually see the data, explore the data, and then get the endpoint. And if you have a very big thread server and you wanna explore it using a Python library, there is this library called Siphon that will definitely make your life easier. Like most scientists, they spin up a thread server, they throw a lot of data in there, and you don't really know where to go to find the data, and there's no high-level way to browse it. With Siphon, you can build your own way to navigate that server. If I have time, I have some extras here. So the first extra, how does this all work? Standards and metadata all the way down. The only way we can find data using high-level queries like that is if we adhere to these kind of standards. The most important one being the climate and forecast standard, but there are others too. So here's a bad example where we're not using these standards in our favor. I'm querying this GUI here using the raw netcdf library. So as you can see, I have to slice all the data. I have to get the time variable. I have to mask manually the bad data. Then I have to create the time interval using the time data using the metadata within this time variable. And the only reason I know how to do this is because it took me several iterations reading the metadata to do that. And then I can produce a plot. But we can do better, right? The good example is using that same URL in Xarray. Xarray will do all that parsing for you behind the curtain. So pretty much it will get high-level dates, it will mask the data, and then you can use high-level slices as well to get the variable of interest, and high-level slices to get a plot. So as you can see, less code, easier to maintain, and easier to read. Do a favor for your future self, start using this kind of stuff. I want to do a break now before I just want to navigate the other notebooks that I have. And how are we on time, Ujung?
You have another 4 minutes.
4 minutes. So I'm just gonna show that here I have many extra notebooks for you all to take a look on data access. Being the most interesting ones, the ArgoPy, which fetches Argo data and create a very custom-made plot about Argo that's at the top layer and one that's at the bottom layer, and create like a year-round plot of temperature. And the other one that's close to my heart, that's very interesting, is, where is it? Did I forget to put it here? I think I did, but this one does something similar, which uses a custom API to get data from the CDS data, it gets SIMD6 from CDS, and then it downloads the data using a brand new thing on NetCDF. Yes, it's this one. I'm sorry. So as you can see, if I try to load this URL using raw NetCDF, I get an error. That's because this URL is not an OpenTap server. It's actually just a file on the web. However, if I append modes equal bytes, now I can actually get that data because it's doing a byte range request. So thanks to the latest NetCDF library, we can get data that are sitting on S3 buckets, for example. How does that work? Magic. And then you can even mix and match with other APIs, like the CSD API. You need some credentials for this. I have them on my computer, but they're free, and you can just go here and apply to it. And then it will return a file sitting on the server. And then you can do the same, even with X-ray. You just put mode equal bytes, and there you go. You get the data, and you can start hacking into the data. So I'm going to stop here now. And do I have time for questions, or should we hand it over to Nick?
We have 2 minutes for questions. So, yeah, Cass, do we have any questions on Slack?
There are no questions right now, no.
So either I was too fast, or I was so perfect that nobody has a question, which is very unlikely.
So maybe we'll hand the time to Nick, and then everyone can direct the questions to Slack. Cool. Thank you, Filipe.
So can we make Ben Tupper host so he can share his screen if that hasn't happened yet?
Oh, that hasn't happened yet. Yes. All right. Should be good now.
Okay, so I'll just hand it off to you, Ben.
Ben, you are muted. Okay.
Hello, everyone. Good to be here. It's good to have a voice. Let me close my door. So I'm Ben Tupper, and I'm a research associate working for Nick Record at Bigelow Laboratory. And I wanted to share with you today a little bit about an overview of how we manage the data. We download a lot of data that we work with on a regular basis, and you know, thinking ahead a little bit and planning really does help in the long run. So there is the issue of data access. There's so many different tools out there available. X-ray looks like a really good one. In the R world, there are other tools that you could also use that are similar, and it's just like mind-boggling. But then you also have to deal with the fact that you're collecting all of this data, and you need to be able to manage it, even for a short-term project, in a way that's organized and easily shared with other people. And it doesn't take a lot of work to think that one through, but it does require some level of work. And we just wanted to share with you some of the very simple tools that we've developed for making that an easier job. Before we get too far into it, I just wanted to point out to you, for anyone who's new or new to R, that there are an awful lot of nice interactive development environments that are wrapped around R. And whether it's on a Macintosh platform, you have R.app, or you're using RStudio, or you just use a command line, or now new to me, using a Jupyter notebook. The important thing to keep in mind is that everything is pointing back to the same computational engine, in this case, of R. It's an open source project, just like Python, and it provides lots of useful tools that work in a really complementary way with Python and a lot of other languages. So do keep that in mind. It's easy to get bogged down in those things if you're not familiar with it. You're really programming in R. We're going to just demonstrate some simple stuff with that. Turning more towards the data, we're going to show an example using data from the Ocean Biology Processing Group, which is a group that NASA supports for serving out their satellite data. And I want to take our browser there just to show it to you. It's a terrific service, and they provide data in a lot of different ways. One way you can access the data is a very simple browser. You can just interact with it. They provide low-level or level 1 and level 2 data, which is basically minimally processed data right off the satellites. And then they also provide a higher level, level 3 browser. And with this, you can go in and look at the data they're serving on a given day. And they provide a rich variety of data available for anyone who's doing ocean biology or any kind of oceanography. By default, it comes up with the platform Modus Aqua and a particular product, chlorophyll, but there's a lot of other products that have come off this platform. And then you can choose, do you want a daily measurement? They provide monthly averages, they provide seasonal climatologies, and then you can also choose either a relatively high resolution or a lower resolution. The other way to access, or one other way to access the same data set is through their threads catalog that Filipe was just talking about. And they have a number of different platforms available to you that you can access through these so-called thread servers. I'm drilling down right now into their level 3 standard map image, and it's broken up by year. So if I grab a particular year, you can see that the data is organized by the day of year. However, as you scan down the list, you see there's a change here. We go from day 001 to, we also have a folder for January 1st. That's because the Ocean Biology Processing Group is slowly going through a transformation in their file naming convention. And so we're going to be abandoning the old Julian day number and switching to this month, day. It's a good change, but it's a change. In our code that we share with you, we shield you from all of that. You don't have to worry about it. But in any one of these days, it has a directory of all the resources available to you. They're all netcdf files. They're all OpenDAP service. So as Filipe was describing, OpenDAP provides a utility, just like with Xarray in a way, where you don't actually have to download all the data. You can actually just say, I would like this little bounding box for this particular time and this product. And it'll reach into the server, grab that chunk for you, and bring it back to you. The other thing I really want to point out to you about the Ocean Biology Group, where's my, here, is the support. There's a lot of people providing data out there, and anyone who's presented so far can share with you their experiences, and it's a wide variety of support level available. But the Ocean Color Group really does a great job with support. The staff there are very prompt with answering questions. There's a terrific forum where both users and the staff answer questions in a really meaningful, polite way. So kudos to them, and it's a great resource to draw upon. That's one reason that I think we can use this as we should use this as an example. So I want to give you a little blueprint of what we're going to be doing, maybe less so today, we only have a few minutes, but more so on Wednesday when my colleague Camille and I do a short presentation on different things you can do. This is the roadmap of what we hope to head towards. So the idea is you're going to do data fetching using OpenDAP. So we're going to have you provide a little bounding box and some dates and types of products you would like. Reach out from either Python, or we're going to use R as a demonstration, to request that data, and it gets sent back to you in memory in your application. Then what you need to do is save that, and we're going to encourage you to save it in a particular style of using directory structures, almost as if it's a database. It's a great way to leverage your computer's organizational ability, and I promise you, you won't regret getting organized when you start out. It'll never come back to bite you later. But in addition to saving these images, and we've chosen TIFF as our destination format when we save it locally, it's also useful to save a little tiny database, and all it is just a tabular data set saved to disk as a CSV file that keeps track of what you are downloading. Because if you're doing a significant project where every day you go and grab more data, well, pretty soon you're going to have to spend a lot of time hunting for that data and figuring out where it is, or filtering it to grab a little subset. So simultaneously keeping a little database going for you, you can leverage that to all of your filtering of what you have downloaded and saved very quickly. So the idea is, after you've done your downloading, some later time, you or a colleague you're sharing this with can then read the database and do very simple filtering, like give me all of the parameters that match chlorophyll A and the period of a month, and you'll get back, either in Pandas or in some kind of tidy thing in R, you'll get back a small table. And the table's going to have variables that you already decided to save in your database. And in this particular case, we get the 12 months that we were trying to filter down on. It's all chlorophyll, it's all monthlies. The next step is to read those in. So you're reading them back into your R or Python memory space, and they emerge as what's called a stack of images. They're geo-registered, meaning your software knows where they are on the globe. And then you can choose what to do next. And so next could be, you just want to, say, line up a buoy location and drill through that stack, getting every one of those chlorophyll values for that location where the buoy is located. Or maybe you just want to do some plots to take a look at them. Or maybe you want to derive some new data doing raster math. All of these capabilities are super easy and available in both R and Python. We also would be remiss if we didn't talk about species data, because there's a lot of data out there on observations people have made, either through systematic surveys or just happenstance. I've seen this, and it gets reported into one of many online databases of species. Those two are available, and Nick has prepared a notebook for that. I can point to it later when I can see it. But there's also a link there, which is a good starting point. It happens to be for R, for grabbing data. Like, I want to know where all the jellyfish have been reported in the world, or a particular type of plankton or something like that. So that's kind of the roadmap of mostly where we're going to be going. I have a few minutes extra. I think I'd like to start what we're going to do on Wednesday, just in case Wednesday takes longer. So I'm moving into the notebook called, it's in the R tutorials directory, and it's 08 Intro to the Ocean Biology Processing Group. I won't go over a lot of the detail that I already spoke about, but I do want to talk about how we store the data, just as an example, and I'd encourage anyone using the ocean biology data to use the same format. But when leveraging these directory structures, the way we look at it is we have some root directory where we want to store our data. Within that, we're going to divide it up into, whoa, where'd it go? There it is. Within that, we divide it into what we call regions, which what that means will be different for every project you're on. For us, it might mean the Gulf of Maine, or it might mean Gulf of Maine level 2 data as opposed to level 3. But beyond that, it's really worth organizing as finely as you can in a logical order, as saving your data. Let's see. We've provided a GitHub package, an R package on GitHub that handles a lot of the functionality. This set of steps here will check to see if you have it installed. It's not actually in the Jupyter install packages, but this will, if you don't have it, it'll reach out and install it for you. The same is true for RGDAL, which I think actually is installed now. And the other thing we do here is we load that library once it's been installed, and we're going to define a path. This is going to define a path in your home directory on your Jupyter environment. And that's where we're going to be storing the data. That's going to be, in a sense, your region. So I'm going to try and run this. Oh, I don't know if it ran. Oh, I guess it did. Okay, and just as an aside, this is an example from Nick Record's lab showing the directory structure we have and a bunch of the files that are in his data directories. Some of them we've downloaded directly from Ocean Biology's database, and others, these here, we've derived those all for our own computational needs. So the next thing we want to do is think about a toy example where we're going to leverage that little Gulf of Maine folder in your home directory. We want to request that we get a small subset of the data. So we define a bounding box. We need to define a series of dates that we want to collect daily data, or sorry, monthly data for. And then we have a function in that package that will build that set of URLs for you. And then we printed out just the first 6, and you can see it's got all the necessary information for you to be able to access those. The next thing we want to do is create a little navigation structure, I call it. It's just a little structure. It has little bits of information that makes it easy to navigate these NetCDF resources. And we have a function that'll build that for you. And last but not least, we now iterate through each one of those URLs we built, of which there's 12, one for each month, and we can go get the data. So you'll notice right here, there's that navigation structure that we built. It just has all the information about the bounding boxes as a convenience. We're also saying, please write it to that path that we already defined, which you're going to find in your home directory. So it doesn't take long to run because we had a, oops, there it goes. These errors, I'm not familiar with what those are, and it doesn't seem to affect anything. It's not even an error, it's some kind of a warning. I've never seen it before, and I'm not too worried about it. This should complete. It's done the first one. Should complete the others. There they are. So if you were to look in your home directory, I'm not sure I can do that. Let's see. Here. There's my Gulf of Maine directory. You should have the same one. There's the little database file it created automatically, or actually we're going to. And there are the folders, the month, day. There's the first file, and then you look in the next month, you'll have the second file, and it's all set up for you. So actually, I jumped the gun a little bit. That database file we can make next, but I want to be aware of the time. How am I doing?
We're at 15, but you can go for maybe a couple of minutes.
Okay, all right. So the next part then is, oh yeah, making the database. So we actually provide tools for that. So it makes it super easy. We could either build them from the full URL string that we made 12 of them, or we could go into that 2018 folder and just do a recursive listing of the files. And that's the way I'm going to show it here. But one thing I want to point out is we're going to use a pipe operator, which is basically a vehicle for passing the output of one function as the input of the next function in line. And that comes from the dplyr package. It's not the only pipe function available in R, but it's probably the one that's most recognizable. So what we're going to do is we're going to first list the files by drilling down into our path, the Gulf of Maine directory. We're going to be looking for files that match this TIFF pattern. We're going to return the full path names, and we're going to do it recursively, meaning drill down into every folder you find. So we take that listing of paths, and we pass it to a function we make called asDatabase. all that does is parse out the name of the files and passes it again to a function called write database, which actually does the database write. And so we do that. And this is the little, what I call a database. It's just a table of data. It's got the original name. And so in a way, it's redundant to split everything out and then save that to a file. But honestly, the amount of time and memory you save on disk isn't worth it. Just do it once and you're done. We find this convenient. The ocean biology names are nicely separated by a dot, the different segments. And that's basically what we split up the database around. So it makes it really easy to say, okay, go get me chlorophyll for daily or monthly or whatever it is using the filtering functions. One thing that we have done with this Oceanhackweek Ocean Biology Processing Group package is we actually provided you with a bigger data set, so you don't have to play just with the Gulf of Maine one. You can also, from the package, read in another larger data set. And the way you do that is we're going to redefine the path. The system file is going to look for whatever we ask it to look for in the namespace for that package. So now instead of our local Gulf of Maine directory, it's going to look in the package directory for a Gulf of Maine directory. And we're just going to read it. And then the other thing I would like to do is sort it by date, because it's got quite a few files in it. And it's kind of a jumble. And so here, this database has both sea surface temperature and chlorophyll. And I think it also has, we can do a quick summary here, take the same database object, and we can do a count. Just tally up how many of the different periods do we have, and of those, how many different parameters are there. And so that's what we get when we do a count, is another little table that tells us, well, you've got 31 SSTs by day, and you've got 12 of all the others. So let's see. The next thing we can do is invoke the Raster function. Raster is one of the tools that's available to you in R for working with geospatial imagery. There are other ones, terrain and stars, and I didn't go into all of them. I didn't want to muddy the waters, but Raster is kind of like the old grandfather of these. So I want to read in par data. I first do that by taking our database, and I'm going to do a filter on it. So I'm going to filter on, oops, picked the wrong example here. This is supposed to be par. Oh, par. And I want monthly par, and I want it just in a certain period of time, May through September, and there are arbitrary dates in May and September. So let's see if that works. There we go. So now we've got 4 files. They're all monthlies, and the dates are between May 15th and September 26th. Now we can actually go get the data using that little database. So we start out by taking our par database, pass it into a function we've written called as file name. That's just to transform it from the database format back to a full pathway. We need to provide it that path where the data is. And then we call the stack function for Raster. It'll provided a list of files, it'll read them in as a stack. Oops, that's not what I meant. I also give them a better name. When they're read in, you get the full name of the file, and it's just gobbledygook. So what we do is we give them more reasonable names. So a raster provides you basic metadata about this geospatial information. You know, the dimensions, how many rows, how many columns, how many cells, that is, individual pixels are there. And this also has 4 layers, one for each of those months. It gives you an idea of the resolution. In this case, it's in degrees. And then the extent, again, it's west, east, south, and then north. And it also gives you some projection information. And then nicely, just as kind of a quick view, you get to see what are the range of values for each one of those. So that kind of brings it to an end of what we were hoping to do in terms of providing an overview of like how you can get data and then how you might store it and then access it later.